Example 6, let's evaluate some factorial expressions. So there's a few tricks that we want to teach you here, and it goes like this. Look at 8 factorial divided by 2 factorial times 6 factorial. Well, here's what I want you to understand. That this guy right here on top is the same as saying 8 times 7 times 6 factorial. So when you see that, then you've got 2 factorial times 6 factorial. That cancels the 6 factorials. And then what we have left here is that we're at now 8 times 7 over 2 times 1. The 8 and the 2 cancel, and that becomes 4. And so we end up with just 4 times 7 is 28. So find the quickest and simplest route to solving some of these things. And so just keep on looking and you'll see it. Here we've got 2 factorial over, and we should say 3 times 2 factorial. And then at the top we have 6 times 5 factorial over 5 factorial. So look at all these things that we've got canceling out. 5 factorials cancel, 2 factorials cancel, and 6 over 3, well, that's just 2. And then, and now we have this with variables. So we've got n factorial over n minus 1 factorial. Well, it stands to reason that n factorial can be written as n times n minus 1 factorial. And so we've got n minus 1 factorial down below. Those cancel. This answer is simply n. So now we're talking about the definition of summation notation. So a convenient notation for the sum of the terms of a finite sequence is referred to as summation notation. We also call it sigma notation. And the reason why is because we use the uppercase Greek letter sigma, which looks like, kind of a capital E right there. And that is sigma, and we use it as a framework to create this thing called sigma notation. So let's just describe it this way. The sum of the first n terms of a sequence can be represented this way, where I is called the index of summation, n is the upper limit of the summation. It identifies the last term that you've added, and the 1 identifies the first term that you add, the lower limit of the summation. So altogether, this sigma with the I equals 1 in the bottom branch and n at the top branch, and then that phrase a sub I makes up the whole sigma notation. So when you use it, this particular one says that this is equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, and on and on and on, succeeding all the way to a sub n. So let's just show as an example how to use then the summation notation for sums. So in this first one, we're looking at a term that's going to propagate this way. See, this is equal to a sub 1 because I is equal to 1. The first term is when I is equal to 1, so 3 times 1 is 3. The next term is going to be when I is equal to 2. So 3 times 2, that's 6. And so we're talking about this was 1, this was 2. The next term is going to be when I is 3, and that's going to be 3 times 3, that's 9. The next term is going to be 12 because that's 4. So 3, 4. And then we're going to finish when we get to the fifth one. So 5 is going to be 5 times 3, that's 15. And so there is the sum. So 3 plus 6 is 9, 9 plus 9 is 18, 18 plus 12 is 30, and plus 15, that's going to be 45. And so that's that summation as it's described. Here's one that's a little bit more complicated. So let's go ahead and evaluate this one. See, when k is equal to, and we actually start with 3. K is equal to 3. So this one's going to be 3 squared is 9 plus 1, that's 10. So the next one is going to be when k is equal to 4. Well, when k is equal to 4, 4 squared is 16, plus 1 is 17. So that's the next one. And then the next one occurs when we're at 5. So 5 squared is 25, plus 1 is 26. And then finally, the last term is going to be when k is equal to 6. So 6 squared is 36. This is going to be 37. Let's see if I can do this quickly. Well, I've got 10 plus 17 is 27, plus 26, that's 53, plus 37, that's 90. So this is all going to equal, if I did my math right, 90. So this one has a starting index of 0, and so we're going to have a 0th term, and that 0th term is going to be 1 divided by 0 factorial. That's just 1 over 1, and so that's 1. So the next one is going to be the first term, so that's going to be 1 divided by 1 factorial. That's also 1, so it's just 1 over 1 is 1. So the next term is going to be the second term. The second term is going to be 1 over 2 times 1. So that's going to be 1/2. And then as we keep on going, we're going to be having to do factorials down below. Now you're going to see that those grow pretty quickly. So the third one is going to be 1 times 2 times 3, that's 6. And then the fourth one, the fourth term is going to be 1 divided by 24. And the next one is going to be the fifth term, and that's going to be 1 divided by 120. And the next one is going to be 6. Now this is going to get a little bit tougher to do the multiplication. So the sixth is going to be 720. And the next one is going to be the seventh term, and that's going to be 1 over 5,040. And the last one is going to be that last term is going to be 1 over 4,320, which is 8 factorial. Okay? And you can add those together. It's a big number, but we're just going to leave it as it is. Okay, moving on to the next thing, properties of sums. I'm just going to talk to this one and just kind of say what this all is. But basically, this is saying that if there was some constant c in the argument of the thing, then it's just going to be, on this particular case, it's going to be n times c is all that it is, and c is just some constant. 2 is saying if I had, and think about this in the distributive property type of terms, if I had c times a sub I, then notice it would just be the same as saying c times sigma of a sub I. And c is just some constant. All that you're doing is you're pulling out, using the distributive property and doing it that way. Well, it also turns out that on number 3, if I had a sub 1 or a sub I and b sub I, and I'm adding them together, that the sum of a sub I plus b sub I is the same as saying the sum of a sub I plus the sum of b sub I. So you could actually figure them out separately and calculate those. Likewise, for the last one, the fourth situation here is that if we have the difference, it's the same idea. That if I took the sum of the difference, then that would equal the sum of the first term minus the sum of the second term. All right, so moving right along then, we're talking about the definition of a series. Consider the infinite sequence a sub 1, a sub 2, a sub 3, all the way through to a sub I, and on and on and on. So that dot, dot, dot means that we just keep on continuing infinitely. And so the sum of the first n terms of the sequence is called a finite series, or the nth partial sum. So we say partial sum because it's not talking about all infinity terms of the sequence, and it's denoted by a sub 1, so this is finite, right, is equal to, and we use that summation notation, just as we talked about it before. But now let's look at number 2. Number 2 says this, that the sum of all the terms of the finite sequence is called an infinite series, and it's denoted by pretty much the same picture, only we have, instead of n at the end, we have infinity. So we can actually put infinity on top of sigma notation, and we have exactly that it's an infinite series being added together. So here's the example 8, finding the sum of a series. So for this series, and find the third partial sum. So let's find the third partial sum, meaning that on top is not infinity but 3. So let's just do that one first, okay? So we're saying that if our sigma ends with a 3 on top and I is equal to 1, and we're talking about 3 over 10 to the I power. All right, so the first term is going to be 3/10, which is 0.3. The second term is going to be 10 to the 2, which is 100. So that's going to be 0.03. The third term is going to be 0.003. Hey, look, when you add them together because of the placeholders, this just looks like this, 3, 3, 3. So that means that if we just kept on doing that infinitely, then our sigma now looks like this, and we're looking at the infinite series. It's going to be 3 over 10 to the I, and that's going to be just simply 0.333 ... which is, we know, the definition of 1/3. And there's ways of proving that that's 1/3, and I'm not going to go through that right now, but we can do that later.